My name is Rafael Marañón. I am a scholar from Andalusia government in South Spain, attending the SDM program. Before coming to MIT, I was working in IT consulting in Spain. And also, I served in projects for the United Nations in New York and the Spanish consulate in Moscow. As this very exciting day comes to a close, with great speaker having spoken about system thinking, it is a great pleasure for me to introduce you our next honorable speaker, Professor John Sterman. As many of you already know, Dr. Sterman is the J.W. Forrester Professor of Management at the MIT School of Management. And he also the director of the MIT System Dynamics Group. Professor Sterman research focused on improving decision-making in complex systems, including corporate strategy, energy policy, public health, and climate change. Professor Sterman has also pioneered the development of management flight simulator and is the author of the award-winning textbooks Business Dynamics. John Sterman has been also our 7-time best professor by student. I have the privilege to work as a teaching assistant for Professor Sterman's System Dynamics Group at MIT. Ladies and gentlemen, let's welcome Professor John Sterman.
Well, thank you. That was a very generous introduction, and I'm delighted to be here with you. Okay, so I'm going to speak to you this afternoon about systems thinking and climate change. And I thought before I start talking, I should hear from you. So we're going to do a little poll, unscientific poll, multiple choice. You have to vote. So I'm going to ask you, excuse me, about your attitudes about climate change. And let me get some water here. So how many of you believe that climate change is a pressing, urgent issue posing grave risks to humanity, and we should immediately take actions to mitigate those risks by lowering greenhouse gas emissions? How many of you think we don't really know for sure, it's important, but we can wait and see, and if it turns out that climate change is going to be much more harmful than we currently expect, then we can take action? And how many of you think that it's just not an issue, that either it's not happening or it's not caused by humans, and therefore there's nothing we can do about it, so there's no need for policy action? A few. Okay. And who didn't vote even though I said you had to vote? All right. Well, so this audience is not typical. If you listen to the opinion polls, what you would find is approximately the reversed proportions, that many people in the United States and in most other countries, including other big emitting countries like China and India, Mexico, Indonesia, etc., significant numbers believe that climate change is happening and that it's important, but most of them think we can wait and see. We don't have majorities who are arguing that it's important, urgent, that we do something about it beginning today. And part of what I want to talk about is why that is and what we can do about it. So let me begin with a very quick review of what's happening in the climate arena. So here what we see is global total emissions of carbon dioxide. There are, of course, other important greenhouse gases, methane, nitrous oxide, fluorocarbon family, black carbon, and others. But this is just carbon dioxide from the burning of fossil fuels in billions of tons, gigatons of carbon per year. And what you can see here, since 1990, it's grown substantially and is currently higher than even the worst-case scenario that the IPCC, the Intergovernmental Panel on Climate Change, considers as inputs to their models to project what the likely future impact of climate change might be. Now, the data I'm showing you up to this point only run through 2008, and we all know the world economy is in a severe recession. Here's the most recent data. Global emissions actually fell, although they remain at or above the worst-case scenario level. Now, what do you think is happening to the concentration of carbon dioxide in the atmosphere? Emissions are going down. Here's another pop quiz for you then. So how many of you think, and you really have to vote, all right? So how many of you think that emissions are going down, so the concentration of carbon dioxide in the atmosphere is still shooting up? How many of you think that it's leveling off in the last year? And how many of you think that it's going down with the emissions? A couple. All right, great. Well, here it is. This is the concentration of carbon dioxide in the atmosphere. It's at 390 parts per million today, which is about 40% above the pre-industrial level. And if you blow this up, yes, it's still rising. So emissions have been falling, but the concentration is still rising. You're a very highly educated group, and I congratulate you. Most of you got it right. Most people get it wrong, and the question is why. Now, the title of my talk, A Banquet of Consequences, refers to a quote from Robert Louis Stevenson that I like very much when he said, "Soon or late, everyone sits down to a banquet of consequences." And so what is the banquet of consequences that we are laying? What will be on the table that we are setting for our children and our grandchildren if these kinds of patterns continue? If emissions keep growing at or above the worst case business as usual scenario that IPCC considers? Well, here's a chart also from IPCC, and what it shows is temperature change, amount of warming we might have by the year 2100 in centigrade and Fahrenheit, and then various impacts on water availability, food production, on ecosystems, on the weather, etc. Now, there's uncertainty about what these impacts might be, hence you see these arrows that span a considerable range. But one thing we know for sure is that as the planet warms, as the average global surface temperature warms, we're going to see increasing risks of these harmful adverse kinds of events. Now, where are we today? We're here. We're already about 0.8 degrees C, or over a degree, about a degree and a half Fahrenheit, above the pre-industrial level. What is the so-called safe level? Well, there is no safe level of warming, but the scientific consensus is that we really need to keep the total global surface temperature warming increment below 2 degrees C, or 3.6 Fahrenheit, in order to avoid the worst risks. And you can see on this chart exactly how that's going to work. If we're at about 2 degrees, we're going to experience rising sea levels, decreasing agricultural production in many developing regions of the world, decreasing water availability. We're already, even today, experiencing the loss of many glaciers around the world, some sea level Arctic ice decay, and some threats to the large ice caps, etc. But if we go much higher than that, the risks become overwhelmingly likely, including sea level rise that would threaten the major world cities, declines in agricultural productivity around the world, much more intense forest fires, droughts, floods, and heat waves, and the possibility of what is now called, without much understanding, tipping points in the climate, whereby we could pass a point such that no matter what we did after that to mitigate our emissions, climate change might then be in a runaway, irreversible mode. So what are the current projections? The most recent study that I think is really strong and rigorous on this topic comes from MIT, from our climate research program here, and here's the projection. The mean estimate is that under business as usual, we'll have over 5 degrees centigrade, or 9.5 degrees Fahrenheit of warming, expected warming, by the year 2100, and it would keep going up after that. Now, there's uncertainty about that, and so I've also shown the 90% confidence interval. The lower bound is 3.5 C, or 6.3 Fahrenheit. In other words, we might get really lucky, and the climate might be more resilient to forcing with anthropogenic greenhouse gases than we currently expect it to be. And if we get lucky, warming would be 3.5 degrees, 6.3 Fahrenheit, or maybe even a little lower. There's a 5% chance that it would be 3.5 C or lower. On the other hand, we might, with equal probability, be very unlucky, and warming could be as high as 7.4 C by 2100, 13.3 Fahrenheit, with a 5% chance it could be even worse than that. you'll notice that that is off the scale of impacts that the IPCC considered in the fourth assessment report. Now, when I present this in this audience, I think you all understand what a 90% confidence interval means. Certainly my students who are in the audience should do. But when you present this in most boardrooms in businesses and in Washington and in other capitals around the world, policymakers often don't understand what that means. So let me put it in plain language. What this means is that we are playing Russian roulette with the future of the climate, with a weapon in which 19 of 20 chambers are loaded. 5% chance that you won't have a live round in the chamber. There's one difference, though, between that story and classical Russian roulette. We're holding the weapon, our finger is on the trigger, but the barrel's not pointed at our head, it's pointed at the heads of our children and grandchildren. So what we have here is a situation in which the best scientific evidence, overwhelming scientific evidence, is that we have an extraordinary set of risks that require concerted action, and nothing is happening. The Copenhagen conference, which I attended, was basically a failure. In a month or so, the next meeting of the UN Framework Convention on Climate Change will be taking place in Cancun, Mexico. And although there's always an expectation management game, right now the thinking is we will be lucky if we can simply prevent backsliding on the non-binding commitments for inadequate emissions reductions that some nations have made. There's no hope for legislation on this issue in the United States at the moment, or likely after the election. And there's no willingness in China or India or Indonesia or the other major emitters around the world to tackle this problem. So why? Well, the conventional thinking about why it is that we have this enormous risk and people just don't seem to care is that, well, you know, it's uncertainty about the causes and impacts of climate change. And the people who believe that, well, we're still not certain, the solution to that is, well, we need more scientific research. I think that's just absolutely wrong. Now, as an MIT faculty member, I'm completely in favor of more scientific research on the climate. We need to do that. But it isn't going to solve the problem. It isn't going to create greater action. Another theory is that it's just too costly to mitigate, to reduce our emissions. I think that's wrong. I'll talk a little bit later about why. The solution to that is maybe more R&D for alternative energy and energy efficiency investment. And you heard about some of the exciting work that's going on in that arena in the earlier talks today. Another theory is that it's a tragedy of the commons, that, well, we can't cut our emissions in the United States or in Europe if China and India and the other developing nations don't cut theirs. The solution for that is we need to capture the externalities, the negative externalities in the environment via global agreements and creating new markets for carbon through cap and trade programs or other means. I think all of these are important. We need more research on the climate. We need more R&D for alternative energy, and we need some agreements, but we can't get any of that done now. Why do we think that just trying to push legislation through or do more research is going to make any additional difference? I have a different theory. No surprise. My theory is that what's underneath all this is a massive failure of systems thinking, and indeed perhaps just thinking, among all the key stakeholders, including the negotiators and the policymakers, business leaders, the media, educators, and the general public. So the solution that I'm going to offer to you, and I don't believe it's sufficient, I do believe it's necessary, is to create meaningful processes and tools that can help all of these people understand for themselves the systems issues that are at stake, so that the distant and delayed and uncertain consequences that create these risks can become more real to people in such a way that they are motivated to take action. This requires that the tools and processes we use are fast, interactive, completely open box, transparent, absolutely rigorously grounded in the available science, but learner-directed and useful to, understandable by any one of the members of any of these stakeholder groups, all the way down to, say, a grade school student. So how are we going to do that? Well, I don't need to give you a primer on the characteristics of complex systems. I think you're all very well aware of how they work. Everything is changing all the time on multiple timescales. Everything's connected to everything else. There's feedback in every one of our systems. They're nonlinear, they self-organize, they adapt, and they evolve. So as the great philosopher Heraclitus said, you can never step in the same river twice. That's, of course, because the river is different and you're different the second time around. In our context, what that means is having intervened in a system once, the system will respond. The other agents will learn and adapt. And the next time you try that intervention, it's not likely to work as well as it might have the first time. This is well known among systems theorists, and by itself, it's not the key problem. The problem is that these characteristics of complex systems are not appreciated in our mental models, in our thinking. Our mental models, in contrast to what you just saw, tend to have extremely short time horizons, like how did our stock do today? Or what are quarterly earnings going to be in the next 3 months? They have very narrow boundaries, silo thinking, as you see here in the picture. People don't understand risk, chance, stochastics. They don't understand feedback, time delays, accumulations or stocks and flows and nonlinearities. And we don't learn naturally about these things because we tend to have very poor intuitive reasoning skills. We're not very good intuitive scientists, and as a result, we often don't learn, or even worse, we often learn things that are downright wrong and harmful. So in our research program here at MIT Sloan, and with my colleagues in other institutions, we have been studying how to improve people's systems thinking skills for well over 20 years now. And I want to share with you a couple of the results of these experiments, and then talk about how we're using those results to try to make a difference at the various stakeholder levels, from policymakers down to students. So one experiment has to do with the accumulation of greenhouse gases in the environment. And I know you can't read this, but we published it a couple of years ago in the journal Science. So let me drop out of PowerPoint, and we'll actually do it. And I expect you're all going to do really terrifically well. Got to get my mouse back. OK, so this is on my website, if I can get my mouse. There we go. And I know you can't read that. It's not important. Let me tell you what it is. You can go to my website later and try it on your own. What we did was we presented subjects of our experiments with a description of how climate change works. The text here is drawn from the IPCC's most recent report, known as AR4, the Fourth Assessment Report, came out in 2007. And in particular, I didn't draw it from the technical report, which is a big document written for scientists by scientists. I drew it from what they call the summary for policymakers. This is the executive summary that's written for policymakers, for the media, for legislative aides, for people who are not PhD climate scientists. And after our students have a chance to read this, with plenty of time to read it, and there's a little data there for you. So that's the historic data for CO2 emissions from 1900 up through 2000. And they read some more about how that works, what the sources of emissions are, what happens to the carbon dioxide once it's in the atmosphere, where does it go. This is the concentration of carbon dioxide in the atmosphere, having risen from 280 in the pre-industrial period to 390 roughly today. And then here's the temperature anomaly showing the warming. And after they've had a chance to read that and ask some questions, then we ask them a very simple question. And there's instructions here, but let me just tell you what's going on. So now we have a hypothetical scenario for the evolution of the concentration of CO2 in the atmosphere. Starting in 1900 up through today, we have historical data. And then stabilizing, a little shy of 450 parts per million. Now, there's a debate about this, but most people believe that if we could stabilize at about 400 to 450 parts per million, we would have a pretty good chance, less than 100%, but a pretty good chance, 50-50. I don't know if you consider that a pretty good chance, but of stabilizing with warming by 2100 at or below that 2-degree level that's considered the maximum. So the question is, what has to happen to emissions in order for this to occur? And so right here on this graph, we have the historic emissions up through today. And the green line is an estimate of the flux of carbon out of the atmosphere. And so where does it go? About half of it, roughly speaking, is taken up by biomass through photosynthesis. And the other half, roughly speaking, dissolves in the ocean, a classic physical chemistry process. So given that, what people are asked to do is to tell me what emissions need to be. Well, this is business as usual, roughly speaking, and that's probably not going to do it. So they drag it wherever they think it should go. Now, we'll just have people raise their hands when they think it's enough. So is that enough? Any hands up? How about this? So I'm just going to drag it slowly down. Raise your hand when you think we've gone far enough. So there's a couple hands going up now at 16 gigatons of carbon per year. More hands? Yeah, more hands. Good. How about down to here? Now, it started at 26, so here we are. We've cut global emissions by half. Any hands? Can I see those hands? All right. How about this? We're down to 10. Can I see those total hands now? Okay, quite a few. How about that? That says we would immediately flatten and stop the growth of emissions. No more emissions growth at all immediately and keep it absolutely constant. How about now? All right. And how about that? And how about that? And how about even lower? Okay, some of you are still not voting. I'm really not happy with that. Well, let me tell you what most people do. Most people do something about like that. Now, let's find out what happens. Well, guess what? The concentration of carbon dioxide just blows right through the 450 level and grows throughout the rest of this century with no end in sight, getting right off the scale. Now, why? What's going on? Those of you who know me or have had me as a student, as a professor in the management school, we cold call our students. So, you know, what's going on? Green shirt right here. Oh, so no, let's get somebody else. So how about it, Martha?
Okay. Well, what's going on is the emissions rate is still above the national removal rate, so that you're continuing to increase the concentration.
Brilliant, exactly right. What she said, if you couldn't hear her, is we're emitting CO2 into the atmosphere, even though it's flattening out far faster than it's being removed. So the amount in the air continues to grow. Congratulations, you're a terrific but absolutely non-typical audience. So at this point, we can just drag it, and it will immediately show us what happens. And we can test Martha's theory. And in fact, when we lower emissions so that it is equal to the removal flux, then and only then do we stabilize, because now we're pouring CO2 into the air at the same rate it's being removed. So if you got that right, congratulations. If you didn't, you're in very good company. Let me show you what most people do. They do something like this. This is from when we administered the experiment on paper. And what this individual did is say, well, I don't really know what net removal is going to be in the future, and why should they? The people who did this experiment are not climate scientists. I didn't expect that they would get that right. But given whatever they said, the green line, in this case the horizontal line of net removal, is, whatever they say it is, then what must emissions do in order to stabilize the concentration? They must fall until those two lines are touching. They must. Now, why is this so obvious and so hard? Well, to get this right, you don't have to have a PhD in climate science. You don't ever have to have studied climate change or the carbon cycle or any of those technical issues. All you have to do is recognize that it's just like a big bathtub. And I mean this quite literally. The amount of carbon dioxide or greenhouse gases in the atmosphere is like a big bathtub. It's being filled up by emissions. It's drained as that carbon is taken on net out of the atmosphere by biomass, photosynthesis, and dissolving in the ocean. And everybody knows that if you pour water into your bathtub faster than it drains out, the amount of water in your tub is going to rise and eventually overflow and cause a big problem in your house. So everybody knows that. But most people can't see it or don't know how it works in the context of the climate. So one of the things that we did is we got this concept of bathtub dynamics out there for folks. And here's another rendering of it that was in National Geographic just about a year ago, the December 2009 issue. And they've done a terrific job rendering the graphic here. And you can see the bathtub, the carbon bathtub, filling up, about 9+ billion tons of carbon going in every year, and just about half of that only being withdrawn, and the tub continually rising, and already over the level we've seen in hundreds of thousands of years. Now, if you understand that, then it's very easy to answer this question. Now, what will the green line do in the future, net removal? Most people, and in my example, I just held it kind of constant. That's not right. Actually, it's likely to fall because there's no drain that just goes away. Basic insight of the system's view, of course, is there is no away. So there are other bathtubs, other carbon sinks absorbing all of that carbon. The ocean saturates, biomass reaches various limits. And so actually, as those carbon sinks fill up, the rate of decline, or the rate of flux out of the atmosphere is likely to decline. But just for simplicity, as most people do, let's assume it goes constant. If you understand the bathtub, it's very easy to understand that you have to lower emissions until they're equal to the removal rate. And it doesn't matter what political party you belong to. It doesn't matter what your training is. This is absolutely unequivocal, because what's at stake here is the principle of conservation of mass, arguably the most basic physical law we have. It is not negotiable. Now, how did people do in my experiment? Well, 84% of them got it wrong. They violated the principle of conservation of mass. 75% of them didn't even get the equilibrium condition right, that emissions have to equal the removal. And almost 2/3 of them asserted, by drawing a graph such as the one that I showed you, that you can continuously emit carbon dioxide at a faster rate than nature can pull it out of the air, and yet the tub will not overflow. Try this at home tonight. See if you can do it. Now, who were these students? Yesterday, I gave a talk on this, and one of the gentlemen in the audience said, well, these must have been random high school dropouts, right? No, these were MIT graduate students. Yeah, I have to say, you know, it's quite embarrassing to have to show this, but that's the way the experiment came out. And what I want to tell you about that is our students are fantastic, especially the ones who are here today. They truly are. It makes teaching at MIT one of the great joys of my life, and I've got no interest in going to any other university. And you know, we all could do that if we wanted to, but the students here are absolutely fantastic. But the implication I take from this is the fact that you may have had calculus in high school and differential equations and linear algebra and control theory and even a PhD in physics, as some of these students did, that doesn't mean that you understand intuitively how a stock and flow system works, even at the level of a single bathtub with one inflow and one outflow and no feedback loops. You don't get that intuitively just because you can crank the math. And so here's the first big failure of systems thinking. And I believe this is something that anyone, anywhere, all the way down to kindergarten can learn. Because guess what? You can actually play with real water in your real bathtub and figure out how this works. And we've done that, and it does work. People usually ask me, well, you know, these are students in your own class. And that's true. And I rush to say, yes, but it was the first day of class. And then they say, well, have you done the experiment at the end of the class? And I used to say, I'm afraid to know the answer. But that's obviously not a scientifically responsible position. So the only thing to do with integrity was to run that experiment. And I'm happy to say that, in fact, people do very much better after they've had even just half a semester of system dynamics. And it has nothing to do with me. It's got to do with the material. And there's an article on that that just came out in the System Dynamics Review. If you're interested, it's on my website. So stocks and flows, accumulation, a major systems thinking failure, and one that's basic and teachable to anyone, you know, even a member of Congress. So what else is going on? Well, one of the other major systems thinking failures that's out there is the inability to recognize and understand how feedback conditions the dynamics of complex systems. So many of you are engineers, I expect. You've had control theory. You understand feedback. The average person doesn't. In our society, if I say, I got some positive feedback today, what does that mean? Yeah, my boss said, good job, keep it up. And if I say, you know, I come home and complain to my wife, I got some really negative feedback today from the dean, what does that mean? It means the dean kicked my rear end for doing something wrong, right? So this is a big problem, because that's not what feedback is, in the sense that I want the public to understand feedback. Feedback are those relationships that cause the decisions we make today to be determined by the state of the system in which we're embedded, and in turn, that state of the system was created by our prior decisions. So there's a continual, iterative, reflexive, self-creating feedback process going on. Well, let's get specific. one of the big problems that we face with systems thinking is everybody now is talking about it. And you can look at speeches of 4-stars and CEOs and many other important folks, and they talk about how a critical capability for success in their organization is to develop our systems thinking capabilities. And that's absolutely true. I believe it completely. It's what I've been trying to teach for my whole career here. But, you know, we've got to make it concrete and operational. We've got to take it past slogans and make it real. Understanding bathtub dynamics, stocks and flows, is one piece of that, and understanding feedback is another. So let's look at an example. Here's a balancing, or in engineering parlance, negative feedback loop. But I got to tell you, for the reasons I just explained, I've given up trying to use the correct technical term of negative feedback with business audiences because they just can't get past the idea that negative feedback is bad. So we call it balancing feedback. And this is a process that is frequently invoked by those who argue that climate change is not important as to why we don't need to worry. And what they say is, listen, as the concentration of carbon dioxide in the atmosphere goes up, it's just going to feed plants faster, and so photosynthesis will accelerate, and that pulls CO2 out of the atmosphere faster, which then draws the level in the atmosphere down. Here's a balancing, self-correcting process. Don't worry, the planet will take care of itself. And in fact, this is true. This is a real process. It's called CO2 fertilization in the carbon cycle literature, and it does in fact happen. However, it's not strong enough to mitigate the problem. And why not? Well, here's another systems thinking skill that you want to develop, and that is expand the boundary of your mental model at every opportunity. So yes, this loop exists. What else might be going on, though, that might prevent this loop from correcting the problem on its own? That's a real question for you. So yeah, what else? So deforestation, which would reduce the amount of area with plants, trees that could generate photosynthesis, that's absolutely happening. And it's a major problem. Right now, forests, net deforestation around the world is contributing 10-ish% of global carbon emissions. So it's a big deal. Not as big as burning coal and oil and gas, but it's a big deal. What else? Yeah, more generally, carbon dioxide, although it's the most important macronutrient for photosynthesis, is not the only thing that plants require to grow. And as you relax the constraint by having more carbon dioxide in the atmosphere, you're going to bump into nonlinear constraints imposed by other nutrients, nitrogen, phosphorus, et cetera, trace nutrients like iron, et cetera, water, sunlight, and so on. And so there are nonlinear limits on this. Furthermore, and we've done experiments, ecologists have done experiments where it's extraordinarily clever. They'll take a plot of experimental forest and install a very sophisticated network of sensors and carbon dioxide injectors so they can elevate the concentration of CO2 in the test plot and compare it to a control plot that's nearby and see if there's actually net biomass enhancement from the elevated CO2. Think about the technical difficulties of doing that. You've got to have a network of sensors that can detect the wind velocity and the CO2 concentration in the ambient air that's constantly blowing through the forest and compensate for it in real time. This is amazing, and they've done it, and the result is, yes, the plants do grow faster, but not all plants grow faster at the same rate. It's just not going to be a little bit lusher. If you remember your high school biology, there's C3 photosynthetic pathways and C4, and different plants grow at different rates. The plants that tend to do best, as it happens, are not the ones we really want for agriculture or other purposes. One of the plants that does the best in elevated CO2 is poison ivy. So there's all kinds of ecological side effects that we can consider as well. Now, the real threat is not these balancing feedback processes. The real threat is reinforcing feedbacks, and here's one of many examples. So here's what happens in this particular feedback process. As the concentration of carbon dioxide and methane, which is a very powerful greenhouse gas, actually far more powerful per mole or per molecule in warming potential than carbon dioxide, though a somewhat shorter lifetime in the atmosphere. As the concentration of these two greenhouse gases rises, it warms the surface of our world. As that occurs, it enhances bacterial respiration. This is the straightforward effect that bacteria and fungi grow faster when it's warmer. This is why you have a refrigerator. And so as a result of that, bacteria munch on their preferred food, which is dead organic matter, and they produce methane if it's anaerobic, say the bottom of a peat bog, and they produce carbon dioxide if it's aerobic. And that then further increases the concentration of methane and carbon dioxide in the atmosphere, which accelerates the warming and leads to still more bacterial respiration and still higher concentrations of methane and carbon dioxide in the atmosphere. This is a reinforcing, or technical term, positive feedback, but there's nothing good about this one. This is a runaway, potentially runaway process, and there are many, many more like this. Now, is this happening, and what can we do about it? Well, the answer is yes, it's happening. It takes a while, but what we know about reinforcing feedback is it looks like nothing's happening at first, but then it gets big very, very fast. This is the same process behind compound interest, and it's the same process behind the financial market meltdown that we've seen since 2008. So think about how that worked. Subprime market starts to go bad, so customers of Lehman Brothers, which had a big exposure to the subprime market, get a little nervous, and they aren't as willing to lend Lehman working capital. So Lehman's financial situation deteriorates. People now are even a little more nervous, so they are even less willing to lend. They pull some of their money out, and so they're even more insolvent, and now people are even more nervous. And that's exactly analogous to this process that you see here, with two differences. In the case of Lehman Brothers, that loop happened with a time constant of weeks to days and ultimately hours, and led to the collapse of that venerable firm and then the demise of your and my life savings. The other big difference between that process in the financial markets and what you see here is nature does not do bailouts. There is no TARP program for the planet if this loop gets out of control. Now, I could show you the data. There have been several important studies published in the last year showing that, in fact, this is happening in boreal forests, in tropical forests, in the permafrost regions of the planet. That's a very big deal because there are thousands of billions of tons of carbon locked away historically in the permafrosts of the world out of the active carbon cycle because they're frozen. And as that permafrost melts, which is already happening, that carbon becomes bioavailable and enters the active carbon cycle. So I could show you all that data, but I think it's more interesting to give you an example. So here's a little video clip of a colleague, Professor Katie Walter, and she's on the left in the blue parka. And she and her graduate students here are standing on the surface of a frozen lake up in Alaska. And, well, I think it speaks for itself, so let's watch.
Oh my God. Here? Here? No, on the side, yeah. Right here. Oh, whoa!
I believe she lost her eyebrows in that. Now, that's methane that's accumulated under the ice of a frozen lake because the permafrost is melted under there and bacteria are munching away, anaerobically producing that methane. Now, feedback is the second big systems thinking failure. People can understand it, but they don't. Well, maybe MIT students don't understand these things until they've taken some systems thinking classes. What about the professional climate policymakers and negotiators? Surely they understand it. Well, this is Cristiana Figueres. She is now the head of the Framework Convention on Climate Change, the top person running the global negotiations. When I first met her, she was the negotiator for Costa Rica. And we asked her, she uses the C-ROADS model, the model that we've developed and I'm going to show you in just a moment, and she likes it very much. And we asked her if she would go on the record as to why she thought it was a tool that was needed. And here's what she had to say. Currently in the negotiation process, the concrete environmental consequences of the various positions are not clear to all of us. There's a dangerous void of understanding of the short and long-term impacts of the espoused unwillingness to act, that is, reduce emissions on behalf of the parties. So, what have we done? Well, what we've done is we've tried to create a set of tools that are easy to use, that are transparent, that run on an ordinary laptop, that are fully documented, open, and available for review and inspection by anyone, that will help people discover for themselves the kinds of systems thinking principles that I've just outlined for you. We call that model, one of the models, C-ROADS. And I'm not going to go into great detail about how it works, but suffice it to say it is a real physics-based model. It has representation of the actual processes in the carbon cycle and the radiative balance of the planet. That is to say, it's not a response surface statistical approximation of larger models. It's a real model. We've calibrated it extensively and carefully to existing scenarios. I'm just going to gloss this right now. All these slides will be available. They're already available on the climateinteractive.org website. What I'm trying to argue is what we've done is we've created a tool that runs instantly and is fully open and available and understandable, and yet behaves exactly the same within statistical limits. There's no material or statistically significant difference between our model and the IPCC ensembles as the large climate models that are used. And those models are wonderful and we need them. But you know, the big supercomputer-based GCMs, general circulation models, and coupled climate carbon cycle models, they take so long to run and they're so opaque to even their builders, and the documentation is not publicly available, that from the point of view of a negotiator who has to respond to a new proposal that's just been put on the table by, say, China, today, they're useless because it takes them weeks to months to run. So we need something that runs instantly, and that's what we've done. And I'm not going to go through any further discussion of whether the model is valid and so forth. This is the fit of the model to sea level. Sea level's been rising because of warming, largely. We also want to make sure that our model is absolutely grounded in the science. So yes, and I'm playing a little fast and loose in view of the time in describing this, but you know, as a scientist, my view is that we cannot step 1 nanometer over the line of what the accepted peer-reviewed science is in this area. And so how did we work to ensure that? A lot of careful calibration, a lot of contact with the climate scientists who build the big models, and we had our model reviewed by a scientific review panel chaired by Dr. Robert Watson, who's the former head of the IPCC, and some very distinguished climate scientists and modelers here. You can read their full report on our website. This is their conclusion, that the model reproduces the response properties of the state-of-the-art 3D models very well, and given that fact and its close alignment with the IPCC scenarios, we support its widespread use among a broad range of users and recommend that it be considered as an official UN tool. Now that hasn't happened yet, although we're hopeful, but it is being used today by the United States negotiators who report to Secretary of State Clinton, operate out of the State Department. The model is also being used in China, in Chinese, running on their own computers. It's a little hard for us to know exactly how they're using it, but they are using it. And what I'd like to do now is take a minute or two and just do a little demonstration with you. So I'm going to close this out. And there are many versions of the model. In the full model, at the request of the State Department negotiators, there are many more nations represented separately and explicitly than you see here. But for the purpose of this demo, we're going to work with a version that has 6 nations or regional blocks. In the full model, in addition to the United States, the European Union, China, India, and then all the other developed nations as one group and all the other developing nations as another group, those are split out. So you have Russia and Japan and Australia and South Korea and South Africa and Brazil and Mexico and Indonesia, et cetera, all represented separately, so that the negotiators at the State Department can pull these sliders, as I'm about to do with you, and represent any proposal that any of those parties bring to the party and immediately get feedback on what might be the response of the climate. So what you see here is the business as usual emissions paths for these 6 regions, US, EU, China, India, all the other developed and all the other developing countries. And we can look here at what the total emissions are for the planet. And they grow substantially, but at a diminishing rate. Now, the underlying assumption about world economic growth is that the GDP of the world continues to grow at pretty much the same rate it's been growing, which is a global average of about 3.5% per year, which doubles every 20 years. And so we've got 4 more doublings plus between now and the end of the century. Well, 4 doublings is a factor of 16 growth in total world real output of goods and services. But emissions, even in the business as usual, no policy case, don't grow anywhere near that much. So already in the BAU case, which comes from IPCC, there's a substantial assumption about technological progress that allows us to reduce the carbon intensity of the energy we use and the energy intensity of our economy so that emissions grow, but nowhere near as fast as the economy. Well, let's go back here. And what we can do now, and by the way, that's an, I believe, over-optimistic assumption. But what we can do now is let's take the United States first. And there are more policy levers in the full model. But for demo purposes, let's just pull this slider and stop the growth of the United States carbon emissions in whatever year that is, 2038. And actually, let's be a lot more aggressive and stop the growth in 2016. And you can see right there, you get immediate feedback. Immediate feedback. The model simulates in less than a second. And the blue line shows that right now, the emissions from the United States stop growing in that year and are completely flat thereafter. And you can immediately see what that does to the projected temperature. It was going up by about 5 degrees C, and now it's a little bit lower. It's quite shocking to people how little it changed. Maybe it is to you. Well, we don't have to assume that the United States emissions stay constant. Let's actually have them start to fall. So I'll pull this slider here. Let's have them start to fall pretty soon. How about in 2020? And at what rate? Well, how about 4.5% per year, just to pick a number. And you see the blue line now reflects that. And this is roughly consistent with what President Obama pledged at Copenhagen. Actually, what he pledged was that we would have about a 20% decline in our emissions. So I'm going to start to decline by 2020. So I'll start to decline a little sooner. And you can see that the unilateral action of the United States would lower the expected amount of warming by a few tenths of a degree C here. Not nothing, but very far away from that 2-degree target. Well, so we can't do it alone. Well, the European Union has, of course, pledged to make very strong reductions, about comparable to ours. So let's stop their emissions growth in 2013, have their decline start pretty soon, about the same. And their emissions, they pledged to fall at about the same rate. So there's the EU's emissions falling. And you can see the difference that it's making to the climate here. And all the other developed nations, Japan, Canada, Australia, et cetera, they're pretty much on board. And if we're willing to do that, they're willing to do it as well. At least that's what they said they would do in Copenhagen. So let's do that, do it this way. We'll have them stop their emissions growth in 2015, which is very, very soon, and have them start a decline shortly thereafter, and at about that same kind of 4 to 5% rate. We're still nowhere near the 2-degree target. It's absolutely clear the developing nations of the world must participate if we have any shot at this. Well, so let's have China get in the game. Now, there are more policy levers in the full model that let us put in any pathway for Chinese emission for any of the countries. But for right now, we'll just do it in a real simple way. They're not going to be able or be willing to stop their emissions growth in the near term because they're bringing hundreds of millions of people up out of poverty. Their economy is growing at a phenomenal rate, and their economy depends heavily on coal. It's going to take them a while, even if they commit themselves completely to doing this. So let's have their emissions stop at around 2030 and maybe begin to decline even by 2060. And at what rate? Well, about the same rate. And now you can see we're still very far away. All the others are going to have to get in the game too. India. And I'm just making up some numbers for right now. This time is short. And all the other developed countries. Developing countries. Africa. Much of Latin America. Etc. So something like that, maybe. We're still nowhere near 2 degrees. So what's going on here? Well, there's global emissions. And there's a couple of kinks there because I wasn't being very careful. It's just a demonstration. But take a look at what's happening with global emissions. They actually peak and fall substantially. Why doesn't the temperature peak and fall? Why doesn't the concentration of carbon dioxide in the atmosphere peak and fall? Well, let's look at that. Here's the concentration of carbon dioxide in the atmosphere under business as usual. It gets up close to 1,000 parts per million. Hasn't been seen in tens of millions of years at least. And when it was seen last, the planet was not one you would have been able to live on. Now it's stabilizing approximately by the end of the time frame here at 600 parts per million. But it's growing all through this century, even though emissions peak in about 2050 and then fall after that. Well, why is that? A lot of people scratch their heads and they don't understand it. And they don't understand it because they don't understand the stocks and flows, as I've just argued. So let's look at how that works. Here's the graph of the two flows. Here's your emissions, and here's your removal. Now, emissions are continuously above your removal all the way until about 2100. So guess what? You're filling the tub faster than it's draining. It's still going to have the level of water rise. And that's why the concentration rises throughout this entire period, and only at the end are you just about in balance. Second thing to notice is, unlike my simple experiment, now that blue curve, which represents the flux of carbon dioxide out of the atmosphere, actually peaks and falls even as we're cutting our emissions. That's because of sink saturation. And as we keep the concentration of carbon dioxide in the atmosphere lower, the ability of the ocean to take up more of it is reduced. Very standard, well-established physical chemistry here. I got to tell you, this is a big, big light bulb moment for a lot of people. And although I'm demonstrating it for you now, the best possible situation for us as the modelers is to have the member of the Senate or policymaker or whoever it might be grab the computer and take the mouse and let me show you what we need to do here, and run the model themselves. And occasionally they do. And when that happens, that is glorious, because now they are in an active learning mode. And I'm not trying to tell them anything. In fact, I believe that without tools like this, there's no hope for developing the systems thinking capabilities or understanding of the climate of any of these constituent stakeholder groups. I don't know how many of you have teenagers, but I have a couple. Well, they're in college now, but sometimes they're still acting like that. I can't teach them anything, right? And I tell you, I tell the students on the first day of my class, I cannot teach you anything. And they all giggle a little bit. And as Raphael was kind enough to tell you, the students at MIT have been generous and given me some teaching awards, so they're all kind of, what do you mean you can't teach us anything? And I say, I'm dead serious. I can't teach you anything. At best, all I can do is create an environment in which you have the opportunity to learn for yourself, and especially on an issue like this. So to make that happen, we need tools that are rigorously grounded in the science and which create an environment for experimentation, since we can't run the experiments on the real climate, and that give you that real-time feedback, let you do those controlled experiments, and that are an environment in which you can control your own learning. Well, there's a lot of other things going on here. I don't want to spend too much time on it. Let me just show you what is going on even in this pretty good scenario. We've made big improvements over business as usual, but temperature is still going through the roof, and sea level, which was rising by about 1 meter by 2100 with no end in sight, is now only rising by 80 centimeters by 2100. Not a lot you can do about sea level once you get that going. By the way, although I haven't emphasized it, there are parameters in the model in this base case, but we don't force those down the throats of our model users. If they don't like our assumptions, which are the IPCC assumptions, they can pull any one of these sliders and many more and see what would happen. So for example, if you believe that that CO2 fertilization process is just stronger than most people believe it is, or if you believe we can somehow enhance it through technological innovation, pull this slider and stimulate the productivity of the biosphere by massive amounts, and sea level will go down in that case. Let me put it back to what it was. Conversely, you can say, well, the historic data that was used to estimate the sea level rise model doesn't include the possibility of rapid collapse of the Greenland or West Antarctic ice sheet. So if we include that possibility, and there's good evidence that that's underway today, so how about maybe just 1 millimeter per year of additional sea level rise per degree of warming? 1 millimeter. So even with our policy now, we'd have 1.5 meters of sea level rise. By the way, if that happens, we have to move the MIT campus. There's no contingency plan to do that right now underway. All right, so we can do a lot more things with the model, but instead, let me tell you a couple more aspects about how the model is being used, and we'll wrap it up and take some questions. So, how's the model being used? Well, we're using it with the policymakers and negotiators of the United States and China, and we welcome other nations. They have an internal capability to use the model. That is, they can run it entirely on their own. We've trained them to do that. In China, it's in Chinese. That means they can modify it if they like. We are available and help them when they ask questions. It's being used in the Framework Convention process to do what's called the adding up work, which is to say, if you take all the pledges that all the nations have made for what they are willing to do with emissions and mitigation and deforestation, add them all up, what would it actually mean for the climate? We're working on that right now as the run-up to the Cancun conference. That's not enough. That is absolutely not enough. I want you to imagine the following scenario. Suppose that instead of having been a big bust, the Copenhagen conference had produced a perfect agreement that every nation of the world at that conference ratified. What would have happened when that treaty, which requires about 80% reduction in global emissions by 2050 with a continuing decline thereafter, what would have happened when that agreement came back to Washington or London or Beijing or New Delhi or Jakarta or Mexico City or any world capital? Dead on arrival. Dead on arrival, because there simply isn't enough public understanding and public support to enable legislators and policymakers to ratify such an agreement. So we're working with the media and the public, and if you go to the website, and I won't show you now, we have a very simple widget that you can embed in your Facebook page, your blog, get it on your smartphone, that shows you at every day what our assessment of that adding up process is. All the nations that have made any kind of pledges, and if they were all fully implemented, what would be the implication for the climate? What I can tell you is base case, business as usual, no action, about 5 degrees C of warming by 2100. If all the pledges that have been made, which are all voluntary right now, were fully implemented, 4 degrees of warming. That's out there. And we're also working with educators, businesses, and other groups in civil society. There's a free version of this model. It's a little more simplified than what I just showed you today, but it's free, available on the web with all the materials you need to use it, and a role-play simulation, which some of the people in the room here have actually played in my sustainability class, and you can ask them about it later. Here's a photograph of students in my class negotiating. They represent different nations of the world, and they negotiate an agreement, and then we test it by running it through the model, as you just saw. And very often, the first round, they come up with a terrible, weak agreement that leaves the planet in desperate straits. Excuse me, planet will be just fine. Humanity will be in desperate straits. Now, people say, well, listen, you bring students into a sustainability class, you have them play a role-play simulation about sustainability and climate change. They're all just going to get together, hold hands, and sing Kumbaya. It's not realistic. So that actually is not what happens, and the reason it's not what happens is we do some things to help them understand their roles and play their roles. So for example, the people playing the role of the developed countries, the rich nations, we sit them down at a table with some beautiful snacks. And the people playing the roles of the least developed nations of the world, I make them sit on the floor, literally. And by the way, we've done this with real policymakers, and one of my colleagues ran it in Sweden about a year or so ago, prior to Copenhagen, and the real president of Micronesia was in that session and sat on the floor. And when the simulated sea level rose about a meter, we cover those people up with a big blue sheet. Covered up the president of Micronesia. He was thrilled. I'm serious, because for the first time, people saw what the implications of sea level rise would be. And guess what? In the simulation, the people who have just been drowned, they don't just sit there. They become climate refugees, and they go and take the food and sit in the chairs of the rich people. And now, for the very first time, some of those people get that it doesn't matter if you live in Denver or Albuquerque, New Mexico, at 5,000 feet above sea level. There is no wall around the United States or any other developed country big enough to protect you from a wave of climate migrants. And furthermore, even if you don't live in a river delta that's likely to be inundated or a low-lying coastal city, it matters to you that the people in the Indus River Valley will be inundated. And we saw what happened in the Indus Valley this summer with the flooding. 60 million people live in that watershed. If they are displaced by climate change, it's on a border between two countries with a history of hot warfare, both of whom have nuclear weapons. That matters to you. This is not something I can tell somebody. It's something they have to discover for themselves. So, at this point in the presentation, where people are recognizing that if we're going to have any shot at all, even a 50-50 chance of limiting warming to 2 degrees, we have to cut global emissions by about 80% by 2050 and continuing down thereafter. Most people are just really depressed because they don't think it's possible. And what they tell me is, listen, that might be what the physics say. It's never going to happen now because it's just too expensive. It's going to hurt the economy, slow down economic growth, and put our country at a disadvantage in trade, and so we can't do anything. I believe every one of those statements is false. And let me quickly show you my reasoning, and we can go into more detail if you like in the Q&A. So I believe if we cut our emissions in the United States, I'll focus on the United States, we would earn a substantial climate dividend. Well, why? We'd have to stop importing oil. That's $1 billion a day we borrow from overseas to feed what President Bush called our addiction to oil. And that hurts the dollar, gives us a big current account deficit, and gives the nations lending us that money substantial leverage over our economic and political policy. It would reduce other harms that we experience from fossil fuels. Here's just one. National Research Council estimated in a study last year that by reducing fossil fuel consumption and therefore ground level VOC, NOx, SOx, and carbon monoxide and other pollutant production, it would save the US economy $120 billion a year in avoided healthcare costs and save 20,000 lives every year. We would also not have to defend our insecure and long variable supply lines for oil. Hard to value that. I'll just say it's priceless. More interesting, I think, investing in emissions reductions is, I believe, the most powerful way to stimulate innovation and new business creation that we have, creating jobs here in this country as well as elsewhere in the world, and gives us the opportunity to at least compete for global leadership in these emerging green technologies. And quite frankly, the United States has already punted this to a large extent. China is winning. I got nothing against China. People in China deserve to rise out of poverty, and they need good jobs just like anyone, anywhere. But in this country, we have punted this opportunity, and China produces more photovoltaics than anybody else in the world, more wind turbines than anybody else in the world. They own lithium-ion battery industry, and they are working very aggressively to further build their lead. Let me show you some real-life examples, and then we'll take some questions. This is Greensburg, Kansas, on the morning of May 5th, 2007. The night before, at about 10:30 in the dark, the town was hit by a Category 5 maximal strength tornado, absolutely devastated. Right here, the high school was a 3-story building, completely destroyed. There was not a single building. Well, that's not true. There was one building left in the whole town. About 13 people were killed, 1,500 total population. So what did they do? Well, they got FEMA assistance and some insurance if they had it, but within 48 hours, they decided to rebuild their town as a green town. And so today, and I was there last month because I felt I needed to see it for myself, it is the greenest town in the United States. This is their community center. It's a LEED Platinum building. They have more LEED Platinum buildings in Greensburg per square meter, or per inhabitant of anywhere on the planet. The steps in the front, by the way, is all that's left of a church after the tornado. They use a high-quality building envelope, ground source heat pump, wind, solar, et cetera. It's quite a lovely building. This is the brand new platinum-rated school, and Randy Fulton there is the principal of the high school. It's a beautiful facility and sustainable all the way through. Just to give you a couple of examples, in the top right corner there, you see the equipment for the ground source heat pumps that are used to heat and cool the building. And in the bottom right, there's a low-flow toilet in the kindergarten. So the kids are going to be learning about what it means to be personally responsible for sustainability right from their first day of class. It's not just the town buildings. This is the John Deere tractor dealership in Greensburg. It was totally wiped out in the tornado. It's been rebuilt as a LEED Platinum building. The tractor showroom and farm equipment part of the business is in the upper left, and Right across the way from it, in the bottom right there, is the new facility where they sell wind turbines and solar panels and other energy efficiency equipment, and that business is booming. Now, you don't have to have your community destroyed by a tornado to make a difference. Here's the new home of the Sloan School. This building, E62, just opened this summer. We moved in just a few months ago. It is the greenest building on the MIT campus. And just to give you a couple of data points, it will use half the energy for lighting per square meter of the MIT average, with better illumination for the occupants, high efficiency lighting, occupancy sensors, et cetera, a lot of daylighting, and 1/3 the energy for heating and cooling per square meter compared to the MIT average through the use of high quality building envelope, great windows, using the solar input, and many other features. We take the waste heat from the refrigerators in the kitchen and use it to preheat hot water, for example. This building will be LEED rated, but until LEED gives us a rating, we don't talk about what level it might be. But it's the greenest building on the MIT campus, and it came in on time and on budget. And people ask me, well, how much more in capital cost did it cost you to do this? And the answer is, if you just look at the property line and draw the mental model around the property line, it's probably a couple % more. But if you draw the line around the total cost to MIT, the answer is negative capital cost increment. And the reason is, with that much of a reduction in its energy consumption, we don't have to expand our cogen plant or our chiller plants to heat it and cool it. That saves MIT money. So capital costs lower, operating costs lower, free money. I'll give you one last example here. This is Building 68. That's the biology building. This building is relatively new. It opened in 1995. Hadn't been really looked at much in terms of its energy consumption. And so last year, the facilities group here went in there, and at a total cost of $150,000, they created energy savings worth $350,000 to $400,000 a year at today's energy prices. That's a payback time of about 4 months. You think you'd like that investment in your portfolio? It's a hell of a lot better yield than the MIT endowment, even when the stock market is booming. So what did they do? Well, they basically did ordinary everyday maintenance that you're supposed to do but hadn't been done. Lubricate the motors, clean out the air ducts. The most important thing is nobody had really looked at the sensors, the thermostats and controls. So you tune those up, and what we found was the building was pulling significant steam and chilled water at the same time. It was heating and cooling itself at the same time. This is routine. Every building in the country, to some extent, suffers from these kinds of problems. And if you fix them, you basically get enormous economic return. There are many, many other examples of this. I'm not going to take the time. Let me just ask what is needed now in order for us to make progress. And what I've been arguing is develop people's systems thinking skills. I believe that's necessary. I don't think it's sufficient. I think what we've got to do is change the basic mental model of how we look at this issue. And especially at a place like MIT, but throughout our society, a very common mental model for how we're going to need to address the climate problem is that we need another Manhattan Project. How many of you have heard this kind of analogy? Yeah, most people. Well, let's unpack that real quickly. How did the Manhattan Project work? Well, the way it worked is, the smartest man in the world, smartest person in the world, right here, wrote a personal letter to the most powerful person in the world in 1939 saying there's some new developments in atomic physics, we better get busy and build us some bombs before our enemies get them. And you know, Roosevelt listened, and by putting enough money and genius in the deserts of New Mexico, in just 6 years, we created nuclear weapons. That's the Trinity test. You can see the appeal of this kind of idea. Give the geeks, give the nerds all the money they need. They'll be happy, and they'll create the technical solution that will allow us to keep living the way we're living, but it'll fix the problem. That cannot work on the climate problem. It absolutely cannot work. And why? Well, just think about this. There was no role for the public. course, the public couldn't know about it for secrecy reasons. But you didn't need the public to participate in it in any way, shape, or form. It could be done with a few tens of thousands of scientists, engineers, and soldiers. Build and deliver the bomb. That can't happen here for climate because everybody, everywhere in the world, is going to have to change the way they use energy, change the way they think about energy, change the way they travel around, maybe change the way they live, where they live relative to where they work, so they're not having to travel so much. Every aspect of our society is going to be transformed, and the public cannot be ignored in that. So I think a far better metaphor, or mental model, if you will, for what we need to do and our challenge is the civil rights movement. Think about this: distributed leadership. No one person in charge. Not even Martin Luther King Jr. was in charge in any sense. He had no positional authority, no elected position, no formal power in our society whatsoever. There was an intricate set of feedback loops between the call for social justice and the people standing up. And what made this work, what made this happen was thousands and then tens of thousands and then hundreds of thousands and ultimately millions of people in this country standing up and marching, registering voters, and demanding that segregation end because it was wrong and racism is immoral. There's a couple of differences between the civil rights movement, though, and the climate change challenge, and these are open questions for us still. First thing is, this took a long time and we're not done yet. And we don't have a lot of time in the climate challenge. Second, and I think more difficult issue is, climate change is distant, it's abstract. There will never be a graph of projected sea level change that has anywhere near the emotional impact of film of a bombed out church or civil rights workers being beaten on the Edmund Pettus Bridge or attacked by dogs had in mobilizing public opinion. We've got to find a way to make it personal and emotional. That's a real research question, by the way. That's where the research should be going, not just in the climate science, but on the science of understanding how people think and feel and behave and what motivates them to get up out of their chairs and off their couches and off Twitter and get out there and do something. Well, can we do it? I believe the answer is absolutely yes, because we've done it before. As long as we're on the topic of civil rights, think about the history of the abolition of slavery and the slave trade. In the 1760s or so, 1770s, 1780s, in England, slavery was legal, the slave trade was legal. Slavery had existed since the beginning of time. Every culture around the world had slaves. In the Bible, slavery is condoned. There was slavery among Native Americans. There was slavery in Asia. There was slavery everywhere, and everybody knew it had always been that way. It was unquestioned that it always would be that way. One of the British slave traders of the day in the mid-1700s wrote that slavery is the hinge upon which all the trade of the world revolves. And people stood up in House of Parliament and said, if the slave trade is banned, the economy will be crippled, England will fade away, because none of our other competitors on the world stage are going to do this. Well, it started with just a couple of people, just a few people who stood up and said, this is wrong and must stop. One of them was a gentleman named Thomas Clarkson. He was a student at Cambridge University. He wrote an essay in order to win a prize in an oratory contest. And the theme of his essay was, is slavery wrong? And he concluded, yes, it was. He won the prize. The essay was in Latin. He won the prize. He then got on his horse after graduation, rode down to London to begin his career as a lawyer. Halfway there, he got off his horse because he realized that if he believed what he wrote, he couldn't do that. He had to spend his life working to end the slave trade. And he found the other people who also thought that way, and they started talking and demonstrating and writing and speaking. And in less than 50 years, slave trade in England was abolished. Something that had always existed and that nobody doubted always would exist. All we're talking about here is finding another way to have hot showers and cold beer. That's got to be a lot easier. We can do this. Thank you very much. So, thank you. I realize that we're a little over the schedule, so I'm happy to take questions if people want to ask questions. If people feel like they need a break and need to leave, that's, of course, completely fine. So, are there any questions? Yes, ma'am. Yeah, so the question is, many people argue that whatever warming may exist is the result of a natural phenomenon and therefore not caused by humans, and therefore there's nothing we can do about it. And what do I think about it, and is it in the model? So it turns out that there are natural sources of variability in the climate, and we don't want to get too technical. You notice that I didn't show you a lot of data and facts and charts, just a little bit to set the stage, but really it was about thinking habits. I think that's where the action is. But to answer your question, it is not possible to explain what has been happening in the climate in terms of decline in ice sheets, the warming pattern, not just the aggregate warming, but the fact that it's more warm at night than it is in the day, and it's more warm in the winter than it is in the summer. It is not possible to explain either the aggregate or micro level features of the data without the impact of anthropogenic greenhouse gases on the climate. It's just not possible in any of the models. And there's good physical reasons. In fact, the natural variability that's out there, which is caused by very tiny fluctuations in the amount of sunlight that hits the Earth due to wobble in the Earth's orbit and some other precession of our perihelion, et cetera, very, very tiny fluctuations in that incoming solar energy, historically, meaning over geological time, has produced very large movements in global surface temperatures. During the last ice age, for example, where right here, where we stand today, there was a mile of ice, the global average surface temperature was only 5 degrees centigrade colder than it is today. And with that enormous sensitivity to very tiny wiggles in incoming solar energy, or forcing by solar insolation, to use a technical term, is evidence of how powerful these feedback processes that I described for you are, because they're amplifying that tiny little change to produce this. And what that means is, by pumping a few tens and hundreds of billion tons of carbon into the atmosphere, we actually are tipping our planet into a regime that's extraordinarily dangerous. Yeah, right back there. Go ahead.
Just thinking about outside the box, I'm not a climate expert, but what's dangerous that we presented is warming, not CO2 in itself. So is there any other way to reverse that, for example, by manufacturing some cooling gases, or, as you were referring to, China getting rid of some of the solar energy?
Yeah, so if I can...
It's not easy to move the Earth out. But I don't know, maybe we can.
This is a great question, and if I can summarize it very briefly, what about geoengineering as a way to cool the planet and or suck some of that carbon dioxide up? So there are a variety of geoengineering schemes that have been proposed. They range from let's put some mirrors in space that would reflect sunlight away from the Earth, to let's spray sulfate aerosols into the upper atmosphere and mimic the effects of volcanic eruptions that we know cool the planet. The sulfates act as little tiny mirrors and reflect light up into space. Carbon sequestration, fertilizing the Southern Ocean with iron to stimulate phytoplankton bloom. There's a variety of others. With two exceptions, I believe all these schemes range from the risky to the ridiculous. And let me very briefly explain. Putting mirrors in space blocks sunlight, destroys agricultural productivity. Now you have starving people, and a little less warming. And then you can't undo it easily. Similarly with sulfate aerosols, injecting sulfate aerosols, which is technically possible at a cost that's very large but within our reach, would cool the climate. There's not much doubt about that. But it doesn't do anything about ocean acidification from elevated CO2. Furthermore, if this works, it creates what economists would call a moral hazard problem, because now people would say, well, we don't have to cut our emissions, but there would be the same range of unintended ecological consequences, declining agricultural production. And I believe some of those risks are absolutely unmitigatable. So let me give you a quick scenario. let's say China, which finds that it's very hard, given their desire to grow their economy and provide jobs for tens of millions of people every year that migrate to the cities, and they really don't want any social unrest. So if they can't cut their energy emissions, their carbon emissions, let's say that they unilaterally decide to launch a sulfate aerosol program. They set up the way you would do this is you would actually launch howitzer shells with artillery guns into the stratosphere loaded with the sulfate, and you could actually do that. They'd set this up in Xinjiang province, say, and unilaterally do this. Well, it probably works. It also changes the amount of sunlight hitting the Earth, and the models suggest that it's likely to disrupt the annual monsoon in South Asia. Whether it does or not makes no difference. The next time the monsoon fails in India and Pakistan, and there are now millions of starving people rioting, India and Pakistan demand of China that you immediately cease and desist. China says no. Now you have a confrontation between 3 nuclear-armed states. That's not a risk that's mitigatable by any technical innovation. And I think similar unintended consequences apply to most all of the other schemes. The only 2 that I think are worth considering, and I don't know that they would really be free of unintended consequences, are white roofs, which would cool our cities and undo the urban heat island effect that's already happened in many places, undo it to some extent, so bring us back to a range that's more approximating normal conditions. That's one. That's worth doing. Doesn't change ocean acidification, but it would help. And the other is biochar. So you would grow biomass. You'd have to do it in a way that doesn't displace food crops. And then you pyrolyze it, so generate some volatile gases that you can use to run a combined cycle gas turbine and make electricity. And what's left after you do that is charcoal, which you can then bury and sequester that carbon. Those are the only 2 that I think have any potential. All the others, like I said, between risky and ridiculous. And let me just make one final analogy on that point. Every one of you knows from your work in business that it is far better for your brand equity, your reputation, your shareholder value, and your net income to prevent the creation of a defect than to try to clean up the mess after that defect has been created and released to the public. Why would we want to focus our energy on cleaning up the mess after we've created the defect? We need to prevent that in the first place. That means emissions reduction, efficiency improvements, green energy. Maybe one more, and yes, sir.
Besides failure of system thinking, what impact do you think the amount of money has been spent to convince people that climate change is not a problem?
So the question is, beyond the systems thinking failures that I described, what about the money, the enormous amounts of money that's being spent to muddy the waters and persuade people that the science is uncertain and we shouldn't do anything? This is a fantastic question. You'll notice that I scrupulously, I hope, stayed away from politics in my presentation. Now, I have a view on this, and I will now share it with you since you asked. And my view is that the scientific community has been enormously ineffective in countering a concerted effort by vested interests who depend on fossil fuels or the products that use fossil fuels to delay action, prevent action, using exactly the same tactics that the tobacco industry used to muddy the waters about the harm that smoking causes. We're not scientifically sure. Until we're sure, we shouldn't take any action. It's not harmful for everybody. That means causality is not clear. A concerted effort to do this, amplified in the echo chamber of kind of ideologically polarized society that we have. And it turns out that many of the organizations and lobbyists and strategists for the denier community also did that work for the tobacco industry. There's a wonderful new book on this by my colleague Naomi Oreskes, where this is all well documented, called Merchants of Doubt, which I recommend to each of you. So the politics of this is a critical part of expanding the boundary of our mental models to think about strategy here. It's very unfortunate that this has become such a politically polarized issue in the United States. And I have to say the blame is not entirely with the conservative side of the aisle. When Vice President Gore chose to make Inconvenient Truth featuring himself only, he polarized the debate. And I've met him, I like him, he gets it, he's an incredibly smart gentleman, he really gets it, and he's completely, personally, passionately committed. But I think it was a huge strategic error for that film to feature only a Democrat, one who is not well liked in the parts of the country like Greensburg, Kansas, that we most need to get on board. Now the exciting thing is, so we should have had Senator McCain or some other well-respected conservative endorsing that equally, and there were such people at that time. Today you can't find a single Republican candidate for the Senate today who accepts that this is an important, real problem. Not one. We've got to overcome that polarization. We've got to get the money out of the politics. Since you asked, we need Congress to act, and somehow we need to undo Citizens United and get the money out of the political process. And I think the systems thinking is relevant in the sense that when a political commentator on any cable news network stands up and says climate change is bunk and CO2 is good for trees, we want the audience out there to understand these processes in the intuitive way that we know they can, so that they simply laugh at that person and ridicule them so that they would no longer be able to make such a ludicrous argument. Let me stop there and thank you very much again.